So question 2 was a car that was braking with a constant dive force at the front of the car, okay? We can represent it with this mass spring damper system with a constant applied force of big mg, big M being the constant mass that's being applied at the front. Okay, we've got a stiffness of 62 kilonewtons per meter. We've got a damping constant of 6 kilonewton seconds per meter, and we've got a mass of 600, which is the mass of the front end of the car. Okay, and the question asked for what is the response of the system. Now we know we've got an equation of motion, mx double dot plus cx dot plus kx is our forcing function, which is a constant, f naught. And we know that the solution to this equation, x of t, is the sum of the complementary function and the particular integral, xcf plus xpi. This is all from chapter 3, okay, so it shouldn't be new. And xcf is simply the free response to this equation. When this equation equals 0, you get the free response. xcf, and this is from chapter 2, is e to the minus zeta omega naught t times by a1 cosine omega d t plus a2 sine omega d t. Okay, that's from chapter 2. That's xcf. And that's the same for any damped system. Okay, it's the free response for this system where there's no forcing function. Now we know that the forcing function is a constant, okay? We've got this car, it's braking, the driver applies a force, applies the braking, such that there's a constant force on the front axle of the car, okay? Front axle can be represented as a mass spring damper, okay, and the constant force can be represented as a rectangular forcing function. Now we went through the process of finding xpi in chapter 2, but we'll quickly do it here. It's a constant force, so we make the assumption that the particular integral is also a constant. I've called it gamma. We don't know the value for gamma. We're going to find it. So x dot pi, or the derivative of gamma with respect to time, is 0. Okay, and obviously the second derivative with gamma with respect to time is also going to be 0. So xpi equals gamma, x dot pi equals 0, and x double dot pi equals 0. And so we take these values and we plug them back into this equation. M 0 plus C 0 plus K gamma equals F naught. And it's quite clear from this equation that therefore gamma must equal minus F naught upon K. Equals F plus F naught upon K. Okay, divide both sides of the equation by K and you get gamma equals F naught upon K. And so the general solution for this equation, xt xcf plus xpi, so we're going to have e to the minus zeta omega naught t a1 cosine omega dt plus a2 sine omega dt plus f naught upon k. That's the general solution for this problem. Okay, and this equation is on your formula sheet. Okay, so that's on the formula sheet. You don't need to worry about having to remember that equation. But what we need to do now, and this is where the challenge comes, is to find out what A1 and A2 are when you've got initial rest conditions, okay? Initial conditions is where you've got x of 0, which is equal to x dot of 0, which are both equal to 0. So there's no displacement, there's no velocity when time is 0. Initial rest conditions. And so we need to apply that to this equation to find out what A1 and A2 are. So let's do that. We take this equation, x of t, but instead of t we've got 0 in here. We've got e to the power of 0, or e to anything to the power of 0 we know is 1, so that disappears. And we've got a1, cosine of 0 we know is 1. Sine of 0 we know is 0, so that disappears. And then we have plus f0 upon k equals 0. Well, that's very straightforward. A1 must therefore be minus f0 upon k. Very straightforward. But now we need to do it when velocity is 0, when time is 0. Velocity when time is 0. And that requires us to differentiate this equation with respect to time. Okay, so let's do that. Before we do that, let's remember that if we take d, and I've got two functions of time, u and v, they're multiplied together, divided by dt. Remember that if we take the derivative of a product, okay, we end up with du by dt times by v plus dv over dt times by u. Okay, remember that's the product rule, and so that's what we've got to follow, because essentially we've got two functions of time. We've got this as a function of time, and this is a function of time. So this could be my u term, this could be my v term, and so we have to do them together. So let's do that. It gets a bit long, but let's stay with me. X dot time is, well, that we've got this term. Derivative of this term is going to be e to the minus zeta omega naught t, okay, times by minus okay. And then inside here we've got this term. That's my v term. So a1 cosine omega dt plus a2 sine omega dt. Okay, so there's the first bit. Plus, and then we've got to take the derivative of this term. Well, derivative of cosine is minus sine, but because we've got an omega d inside the function, then that comes out. So we have minus a1 omega d sine omega dt plus a2 omega d cosine omega dt. Okay, and what I've done is I've taken this e to the exponential term outside of the brackets because it's multiplied by both of those terms. So if you look at it, we've got this bit here, that's our du dt multiplied by v, okay? And here I've got my u by dv by dt, okay? And what I'm going to do is I'm going to rearrange this term, grouping the cosine and sine terms up together, because that aids what we're doing. So leave this outside, let's not worry about that at the moment. Okay, and we've got cosine omega dt times by, we've got, over here we've got a minus a1, a plus a2 omega d, and here we've got a minus zeta omega naught a1. So that's the cosine terms, and then we do the same thing with the sine terms. I'll put a minus sign in here just it makes things easier, omega dt. And then we've got, over here we've got a minus a2 zeta omega naught, but because I've taken the minus out, that's plus. So zeta omega naught a2. And over here we've got a minus a1 omega naught. So that, because the minus has come out, that becomes plus a1 omega naught, omega d, right. And we know that when t is 0, so x dot of 0, we know that that equals 0. Well, this term obviously drops to 1, so let's not worry about that. We end up having cosine. Cosine of 0 is 1, so we have this term, a2 omega d minus zeta omega naught a2. Sorry, a1. Yeah, that's right, a1. And sine of 0 is 0, so that term disappears. So we end up with this term must equal 0. Now we know a1, we found a1, that's minus f naught upon k, so we have a2 omega d plus zeta omega naught f naught upon k equals 0. So therefore a2 equals zeta omega naught divided by omega d f naught upon k, and that's a minus sign in there because it's moved to the other side. So does everybody follow the differentiation that we've done? Okay? We have to take the derivative of a function with respect to time, okay, and the function is itself two functions of time. We've got an exponential with t in there, and we've got a sinusoid of omega dt, okay? And so we have to use the product rule, okay? And so that's what I've done. So the first step was to use the product rule, okay? This term is constant to both of these, but we've got the derivative of the exponential times by our sinusoid, and then we have the derivative of the sinusoid times by the exponential. Done a rearranging to group the sine and cosine terms together, and then when I stick in t equals 0, the exponential reduces to 1, okay, and the cosine of 0 becomes 1 as well, so we keep this coefficient, and then sine of 0 is 0, so that disappears. We set the whole thing equal to 0, and we rearrange solving to get a2. So now our general solution, which we had up here, we can rewrite xt equals e to the minus zeta omega naught t, and then we have our a1, which is f naught minus f naught upon k, cosine omega dt, and then plus a2, well that's minus zeta omega naught over omega d f naught upon k sine omega dt plus f naught upon k. Obviously that f naught upon k term disappears when you take the derivative because it's not a function of time. So the derivative of a constant we know is 0. And so here's our equation, and we can write this in a much nicer form. Notice that each term has an f naught upon k in, so I'm going to take that out, f naught upon k, and then we have 1 minus, and then I'm going to put these in brackets because it helps. E to the minus zeta omega naught t cosine omega dt plus zeta omega naught over omega d sine omega dt. So that is the solution. At this point, you can go back to the solution you did last week because it's simply a matter of plugging in numbers. We work out what f naught upon k is, work out what omega naught is, omega d, and zeta, which you can all do. That's a minus sign, by the way. And you can plug in the numbers, but let's quickly just do that. F naught, 1.4717 times 10 to the 3 newtons. Omega naught was 10.1653 radians per second. Zeta came out to be 0.4919, and omega d was 8.8506 radians per second. And we also know that zeta omega naught is helpful because it's in there and here. Well, that's going to be 5 radians per second, okay? And f naught upon k, which is at the front, came out to be 0.0237 meters. And so you can plug in these terms into this equation to get the total solution. X of t, 0.0237, 1 minus e to the minus 5t, cosine 8.8506t, plus, and then we have 5 divided by that, which gives us 0.5650 sine of 8.8506t. And there is the final solution with the numbers plugged in. We have a decaying exponential times by a sinusoid. So we know that the sinusoid is going to decay back down to 0. When time goes to minus infinity, this term drops to 0, so the sinusoid completely disappears, and we have a solution of a constant value, which makes sense if you think about it. We're applying a constant value to a damped system. Okay, so the damped system is going to move, and it's going to oscillate for a little bit, but that oscillation is going to die away. And at which point, if that force is still being applied, you're going to end up at that value, at a constant value. Okay, the static displacement. But because we've got the transients in here, we've got a sinusoid that's going to start oscillating when you apply the force. But because of this exponential, because it's damped, it's going to die away. Okay? And when it dies away, when e approaches e to the power of minus infinity, approaches 0, you end up with 1 times by that constant value, which makes perfect sense. And so what I'm going to do is I'm going to move to Matlab and just show you the solution, okay? So here you can see, I'll just talk you through, there's a bunch of closing commands and clearing commands up here. There's my parameters, so there's my stiffness, 62 times 10 to the 3, damping, mass, applied mass, g, and then obviously F naught is m times g. Then I work out what omega naught is, zeta and omega d is, define my time domain, initialize x, and you do that outside of the loop for speed, and then I've got a loop here that goes round and populates my vector in the sense of x for each value of t. And so I go along, and you can see I can multiply out. And that's my equation, f naught upon k times by 1 minus the exponential, exp minus zeta omega naught times psi t, okay, times by the sinusoid. So there's the cosine term, and there's the sine term, okay. And then down here I've got some plotting commands. So if I press go, you can see that this is the result that it gives. Okay, we start out at 0, down here, okay. The constant force is therefore then applied, and the thing starts to oscillate. So you can see it overshooting, and it goes back down below the value, and then it ends up settling. And that's because there's quite high damping in this system. Okay, if we went back to the solution and changed the damping, let's reduce the damping to, say, I don't know, 3 kilonewtons seconds per meter, and you run the command again, you end up getting more oscillations, which makes sense. Okay, and obviously you could therefore, you could even reduce the damping down to 0. And notice what that does. That means that this term here, zeta, becomes 0, so the sine term just disappears, and you end up with a solution for the case when you've got no damping, and you end up with this case, which you've seen before in some of the solutions to the problems that you've had. It oscillates up and down. The centre point is 0.0237, the constant value, but it oscillates 2 times that back to 0, 2 times that back to 0, and so on. And we'll do that forever because there's no damping. Okay, so that's the solution to that problem.